Okay, so we're gonna focus on binary relations. And what does binary mean? It means that it's a relation between two sets, just two, right? In general, relations could be between, two, three, four, five, however many sets, okay? Now, we're also going to focus on binary relations where the two sets are actually identical. So we're looking at a relation that goes from a set S to a set S, the same set, okay? And our first word is reflexive. This is a property, okay? And we say that something is reflexive if x comma x belongs to R for all x in X. Another way of saying that is that x Rx is always true, okay? So that's the definition. That's what it means to be reflexive, okay? Now, another definition is symmetric, okay? And what it means to be symmetric is that whenever you have y comma x, then you also have x comma y in the set, okay? So again, and another way of simply looking at that is to say this, x r y if and only if y r x, okay? So that's what it means to be symmetric. And we also have anti-symmetric. And anti-symmetric is somewhat similar to symmetric, and intuitively what you want to say is that xry and yrx can't both be true, but it's a little bit different because that only holds for different x and y. In math, one of the ways that we can actually say this is like this. If x comma y belongs to R and y comma x belongs to R, that we don't expect that to happen for different y's, x and y's. So if it does happen, then we can conclude that x is equal to y. Okay, this allows, for example, x less than or equal to y, where less than or equal to y is our relation. That allows that to be anti-symmetric, because if x less than or equal to y and y is less than or equal to x, well then x is actually equal to y. That's permitted. Okay, so these are some properties that we have. There's another one, and that is transitivity. Okay, so with transitive, what we have is that if x is related to y and y is related to z, right? Well, that simply implies that x is related to z. Okay, that's what we mean by transitivity, and like less than or equal to is transitive, equal is transitive, and so on. Okay, so these are all definitions of properties that relations can have. And just to quickly summarize here, so you don't forget these: reflexive, that means that x is equal to x, right? X is related to x. Symmetric, that means if x is related to y, then y is also related to x. And transitive, if x is related to y and y is related to z, then x is related to z, right? And we also have the antis. So we have anti-reflexive, x is never related to x. Anti-symmetric, if x is related to y and y is related to x, then it must be equal, because we don't allow that to happen for different x and y's. Okay, so let's look at some examples of binary relations and how they have these properties. So we'll start with the relation less than or equal to on the integers. And we see that it has to be reflexive because x is always less than or equal to x, right? So reflexivity is taken care of. How about symmetry? Well, it's certainly not symmetric, right? X is less than or equal to y does not necessarily mean that y should be less than or equal to x. So it is not symmetric. In fact, it's anti-symmetric. And that's because if x is less than or equal to y and y is less than or equal to x, then it must be the case that x is actually equal to y, right? That's the only way for both of those to be true. So we get anti-symmetry. And transitivity, that's pretty easy. If x is less than or equal to y and y is less than or equal to z, then absolutely x is less than or equal to z, okay? So yeah, we have that. Let's see. How about less than? Well, that's very, very similar, right? But notice what we don't have. We do have transitivity. X is less than y is less than z, x is less than z. Awesome, right? We actually also have anti-symmetry, right? Because x is less than y and y is less than x actually can't both be true, right? It's impossible. So since x is less than y and y is less than x is false, then that implies anything, right? So that implies that x is equal to y. No problems. That's true. So we have there anti-symmetry. Okay, it's actually my preferred form of anti-symmetry. I kind of like it that if x is less than y, then that means that y can't be less than x. Okay, reflexivity. X is never less than x. Okay, so that one's done. That one is actually, I mean, it's not reflexive. Okay. Here's some more informal definition. How about ancestor of? Okay. Well, that's also transitive. If x is an ancestor of y and y is an ancestor of z, then definitely x is an ancestor of z. Okay. So transitive is easy. Anti-symmetric, definitely. If x is an ancestor of y can't possibly be an ancestor of x because it was born after x, right? So that's very true. It's anti-symmetric. And notice formally what we have is x ancestor of y and y ancestor of x. That's false, so that implies anything. Okay. And what about reflexivity? Well, no, right? Nobody's an ancestor of him or herself, so that's done, right? How about parent? Okay. Well, parent again, reflexivity won't happen because nobody is their own parent, right? How about transitivity? No. X is a parent of y, y is a parent of z. That means that x is a grandparent of z, not parent. So it's actually not at all transitive, okay? Anti-symmetric, yeah. So if A is a parent of B, that automatically means that B can't possibly be a parent of A, right? Nobody can be a parent of their own parent. So yeah, that's done. Okay, and then there's sibling. Sibling is a little subtle because nobody is their own sibling, right? We don't think of that when we think of siblings. So it is the case that if x is a sibling of y, then y is definitely a sibling of x. Okay, it is symmetric, right? On the other hand, it can't be transitive because if x is a sibling of y, y is a sibling of z. We cannot conclude that x is a sibling of z. Like for example, if x is a sibling of y, then y is a sibling of x, right? Since we just said that it was symmetric. And if it was transitive as well, then x would have to be a sibling of x. And we said, no, that never happens. So right there we have several different relations. And you can see how the properties are defined in each case.